Okay. Good morning, everyone. I want to welcome you to another statistical machine learning class. Of course, on Monday we started graphical lasso, and of course, today we're going to continue, from doing that. I want to walk us through what I call the Blockwise coordinate descent application, or this particular approach is used to estimate your precision matrix. Of course, before now, we are interested in obtaining precision matrix. Why is precision matrix important? Is because precision matrix enable us to measure direct dependency, okay, among variables. Okay, with precision matrix, we'll be able to isolate indirect effects, okay, from the network. When you isolate indirect effects, of course, the edges between the variables will disappear and making your network sparse. When your network is sparse, then your network it become more interpretable. So the approach that we actually going to use is called the Blockwise coordinate descent, and that's why we want to focus on that in this lecture. Okay, the very first, if you look at what I'm projecting now, why do we need graphical lasso? Okay, of course, you are actually using graphical structure in the first place because we believe variables are related by network. And of course, the lasso is going to come in. The lasso will do the job of sparsity. It's going to shrink. Because lasso comes with penalty. It's going to shrink any weaker relationship to zero. Now, in that situation, we're actually going to say, after observing the rest of the variables, two variables are conditionally independent. So when conditional independence is involved, then you're actually going to see edges disappearing. As you can see here now, between 3 and 4, there's no any edges, there's no any arrow. So that is actually saying variable 3 and 4 are conditionally independent given the rest. So what is important here? We want our graph to be sparse. We don't want it to be dense. A sparse graph has more interpretable structure. So a sparse graph translates into fewer edges. The fewer edges translate into easier interpretation and better regularization. What is the goal of a graphical lasso? The goal is to estimate precision matrix. Precision matrix is actually the inverse of the covariance matrix. I told you the other time, reason why we cannot get satisfied with the covariance matrix. Why do we need to find the inverse of the covariance matrix? Because the covariance matrix actually we mess things up. The covariance matrix will give us a combination of both indirect and the direct effects. That we don't want that, because the indirect effect is what make the network to be complicated. And what we need to do, the moment we find the inverse, provided if the covariance is stable. If the covariance is stable, you'll be able to get your precision matrix is going to be great. But if it is unstable, then you cannot just find the inverse. In fact, inverse may not even exist because the determinant, the situation where there is a perfect multicollinearity among the variables, we expect the determinant of the covariance to be zero, to be singular. And when that becomes singular, the inverse doesn't exist. When the inverse doesn't exist, then it means the precision matrix, you may not be able to get that. Okay? But I'm actually going to walk us through what we can do in a high-dimensional data where the covariance is expected to be unstable. What can we do? And that's why we need the idea of a lasso coming in. Okay, so the precision matrix actually helps us build a sparse model. Now, if I now want to, based on what I show you on Monday, we use the method of maximum likelihood. To be able to use the method of maximum likelihood, we actually started from multivariate normal distribution. Now, from the multivariate normal distribution, wherever we see the inverse of the covariance, we're actually going to plug in precision matrix. The precision matrix is this guy here. That is a precision matrix. Okay. Now, when you plug in the precision matrix and you simplify that and you get rid of the constant, initially this is what we're going to have. I explained to you this. When I find the maximum likelihood of this guy by differentiation, when I differentiate, the log of something, it should give me 1 over, right? It should give me this, right? Which is this, right? Which is this, which is this inverse, right? Okay, and from here, because I'm differentiating with respect to the precision matrix, I'm actually going to get that. And when I equate this one to 0, you know what it's telling me? It's trying to say this equal this. So it's trying to say the inverse of the precision matrix is a covariance, and at the same time, the inverse of the covariance is a precision matrix. But I'm only going to get this, I'm only going to use this in a situation where the number of observations is more than the numbers of features. If the number of observations is more than the numbers of features, I expect the MLE to behave well, because MLE has a property asymptotically, it requires you to have a large sample size. But what if in a situation, in high-dimensional data, where this is much more n, the numbers of features is much more greater than the number of observations, then using maximum likelihood based on this only, it's not going to give us a unique solution. Because of that, we actually need a parameter from lasso that we're going to bring in. That's why you have that guy coming in. Okay, so each of these time has the role they play. Okay, if I want to know how the model fits the data, that is going to tell me the trace of that to tell me. If I want to know stability, then the log of determinants of precision matrix is going to tell me. But if I want to enforce sparsity, I want to have a simpler network that will be that can be easily interpreted, then I need to include a penary from lasso. Okay, so this a whole thing is what Friedman, Astin, and Steve Sharani 2008 look into. Is there any question before I move forward? Is there any question? Everybody good, right? Okay, we are counting down. Final. Okay. Now, uh, of course, because we actually seeking want to maximize seeking the value of the parameter, that we maximize the likelihood. We're going to go by way of optimization. And of course, what we're going to do, we differentiate, right? Okay, differentiate that. You have that. Differentiate that. You have that. And this is going to come, that's an indication that I want to differentiate that. Okay? So if you take a look at that, that is going to be the first order optimality condition that we believe all of this lies in zero. We believe that, what that guy mean is zero lies in that. Okay? And you know what? If I have something like this, it's not going to be a closed form solution. Okay? We can't solve this directly. Please pay attention. We cannot solve that directly. And that is the reason why that's why the topic is called Blockwise. Because we can't solve it directly, it's going to be so hard to solve, to figure out. So what I'm going to do is what Teshurani and the like did in 2008. They used a method of a blockwise coordinate where they split, okay? And they now handle that one at a time. So that's why we call it blockwise coordinate descent. Now, you can say we don't just do what we do. So take a look at this. I said, why not solve directly? Somebody may ask, why is it that we can't solve it directly? Because for high dimensional optimization will be a problem for high dimension generally. Okay? And the challenge is going to be solving all the entries of the precision matrix at once. It's actually going to be computationally expensive. Okay? Because of that, we're going to use a blockwise coordinate descent. Okay? Now, let's see what is going on here. Please pay attention to be able to see what is going on here. Okay? If I have so many variables, I'm actually going to take them one at a time, okay, where I'm actually going to work on one variable. Then I will look at the relationship of that one variable with others. Now, please pay attention. We're getting there now, okay? I want you to explain the idea behind the blockwise coordinate descent. Number one, we pick one variable at a time. You got several variables. You're going to pick one variable at a time. Then you separate that variable from others. You update, okay, only its row or column, okay? Then after you're done with the updating, you're going to go to the next variable, then you repeat until the matrix stabilizes, okay? That is the approach. So, like I said, instead of us to actually, give me 1 second. So instead of us to actually, solve the whole problem at once, okay? Because that's going to be a very huge, or it's going to be a cumbersome task for us. Then we're actually going to solve this using, solve many smaller problems. We break it into pieces. Okay, I'm moving. Now, this is the idea that I just talked about. The strategy is to break the matrix into smaller pieces. Then we now solve one at a time. We start updating. Okay? So I'm going to show you, I think I have an example that, okay, this is not, it's not showing here. We want to consider a one variable at a time versus the rest. Now, the question is, how am I going to, I think I put this on the material on Monday. Oh, sorry, this one is not, this actually cut off, but let me go back to, 1 second. Okay, let me come back to this material. I'm going to show you the particular place so that you can see it clearly. Okay, right here. Can you see now? This is it here. That is the splitting that I talk about. But for you to be able to understand this splitting, you know what I'm going to do? I will walk you through an example. So let me go. So take a look at this. This is the splitting. We are splitting precision. This is precision. This is the sample covariance. This is the working covariance. We have the working covariance. We have the sample covariance. Okay, we're going to get a working covariance W from the sample covariance. Okay, we're actually going to use the working covariance after it has already stabilized. Then we're going to use it to estimate the precision matrix that we want. But you know what I want us to do? I think I'm going to walk us through an example. Okay, so let's keep moving. Now, I want to walk us through an example. Please pay attention. Are you ready? Okay, let me show you how we partition the matrix. I want to show you how we partition the precision matrix. Now, it's going to come in this form. Where this guy here, the first one here, that represents all other variables. You know, I said, if let's say if you have 3 variables, you will start with the first with 1. Okay, you're going to look at that versus the rest. So that theta 1 1 represent all other variables that I'm not updating now. Then if you take a look at this guy is this guy. It's just the transpose, right? So that guy is the relationship of the variable you are updating with the others. Please pay attention. If you don't understand, ask me a question. Relationship with others. Then this guy here, then is talking about its own variance. The variance of the variable you're trying to update. Okay? Please pay attention to that. Now, for you to understand, I want to be practical. Please pay attention. I want to use small read data example, even though there's going to be so many features, but I just want to demonstrate to you. Okay, having so many features, algorithm is going to, but I just want to explain what is behind the algorithm. I need you to pay attention because these are typical exam questions. Okay, now let's say we have 3 variables: height, weight, and blood pressure. We got 3 features. Okay, and this is the data frame. We got this from 5 people. We are here. Okay, this is for number 1 person, number 2, number 3, number 4, number 5. We collected height, data on height, on weight, and on blood pressure. So which means the first row here, okay, I have the height of the of number 1 person, I have the weight, and I have the blood pressure. So this is a data matrix X. Now from the data matrix X, because I have 3 variables, now I can get a covariance. The covariance will be 3 by 3. Please pay attention. Can you see my covariance now? Of course, you know how you can get a covariance. We've done that before. Of course, this covariance now, okay, of course, you know, in the diagonal of the covariance matrix, this will be the variances, right? Okay, half diagonal will be the covariance, right? Okay, now, so if you take a look at, for instance, what here, X11, this is going to be S11, which is the variance of height. This is the variance of weight. This is the variance of blood pressure. But then after that, if you cancel this and you want to talk about all of these, you're talking about the covariances. Okay, I can talk about, I can talk about, for instance, X12. Okay, I can talk about if you take a look at this guy, it is the covariance between the height and weight. Then I'm also going to have the covariance between the height and blood pressure. Then I'm still going to have a covariance between the blood pressure and weight and so on like that. Now, after that, please pay attention. Okay? I'm just using this as an example to understand the block descent I'm talking about. Now, and I want to partition. I want to partition now. Okay? Now, what I'm going to do here, what I'm doing now in the partition, you can see this is the, suppose I want to start with blood pressure. You know, I said I'm going to take the variable one at a time. That was what I said. If I choose a variable S3, what do you think I'm going to do? What I'm actually going to do, if I'm actually going to come back, I'm going to go back here. Okay, then I will strike this out. I'm only going to have 2 by 2 because I want to update X3. It's like I'm removing the S3. Okay, when I remove that, please pay attention. If you don't understand, ask me a question. When I remove that, you're going to see what I'm actually, this is what I have now. Can you see that? I've removed anything in the covariance matrix that has to do with S3. And after removing that, we are left with this. Okay? Now, I want you to pay attention to something. If you look at this guy here, okay, is the one I'm focusing on here. The X12 is this guy. Okay? You know, if you the X12, okay, is how the X12 give you the covariance, the one that I removed, the one that connects S3 that you're focusing on to X1 and S2. Now, you know, some of you may be wondering, where do I get the 1.5, 1.5? Please pay attention. Can you see that? Here. Can you see that? It's like, this is what we did. We partitioned this. Like that. Because this one is the same thing as that one. Right? It's like we are partitioning to 3. Because this guy is the same thing as that one. So this guy, we want to focus on that separately. This guy, do you know, can somebody tell me what that 1.3 means? That 1.3 is the variance of the variable that I'm focusing on right now. I'm focusing on S3, right? And that was why, please pay attention. Okay? And that was why, now you now see this. You now see what I'm doing here. Okay? I'm trying to explain here. Take a look at that. Okay? The X11, okay, if you take a look at this guy here, that gives the covariance among X1 and S2, right? That's a covariance among the variable I'm not updating at the moment. This guy, the covariance between the variable I'm updating and the one I'm not updating. This guy, it is the variance of the variable I'm updating. Is there any question for me? Any question for me? You get that, right? Okay. Now, the next thing I'm actually going to do, okay, I think I've already done that. Then I will do the same to precision, okay. Now, why this help computationally? Of course, I think I've explained before. Instead of looking at it as a whole, will be very, very difficult to figure out. Then we actually split, you know, we break it into pieces and we update one at a time. We have an algorithm that's going to handle that for you in R. Okay. Now, what is the connection to lasso regression? I need you to pay attention, okay? What is the connection to lasso regression? You know, the beta, if you take a look at what I said here, the beta will represent relationship between the choosing variable that you are trying to update in right now with the others. Okay? That is what the beta. And let me tell you this. If the relationship is indirect, you know what will happen? That beta will be 0. Does that make sense? But if the relationship is direct, it's going to be non-zero. Okay? Now, what is W11? Please pay attention. And that will come from your current working covariance estimate. Now, I'm going to show you the way the algorithm is going to, the working covariance is actually going to be different from, sample covariance. Let me write the working covariance for you. Now, based on this data now, if this is X, I need a working covariance. Because I'm not going to use the covariance of the data. The covariance because I don't want to tamper with the original relationship in the data. But you know what I'm going to do? The algorithm is actually going to shift the diagonal up, because by adding lambda, shifting diagonal up, meaning that here, this one, we don't update anything in the diagonal. You know why we don't update things in the diagonal? Because these are the variances. We don't want to tamper with them. What do you think we are updating? We're updating the covariance relationship that exists between two variables. That's what we're trying to update. Okay? So what we're going to do is we're going to add that to lambda high. Situation where we have 3 by 3. Okay, I is going to be an identity where we're going to have 1 0 0 0 1 0 or 0 0 1, right? Now, lambda high, you multiply this by lambda, then we add it to this. When we add it to this, it's only going to add something to the diagonal. And the reason for adding something, because if you take a look at this now, okay, like I said your W is sample covariance plus lambda high. Then you need to be able to figure out the lambda, because when your lambda is large, okay, you are actually going to shrink more relationship to 0. When your lambda is small, then you are not likely going to shrink more relationship to 0. So we don't choose lambda arbitrarily. Okay, we optimally, we know what we're going to do on Friday. You're actually going to see how we can choose lambda by cross-validation. Has anybody heard about cross-validation? Okay, so I'm just explaining that. Okay, so we have a sample covariance, we have a working covariance. Working covariance, we derive that from sample covariance. Okay, so I think I've explained all of this. So the connection to lasso regression, the lambda here is the one that is a sparsity parameter. Any relationship that is weak is going to shrink that to 0. An indirect relationship is going to be weak. We don't want indirect relationship. It will actually remove indirect relationship, making the network sparse, which is our goal anyway. If the network is sparse, then we have more interpretable structure. Okay, so suppose after we updating S3, I'm just assuming, and we obtain this. Please pay attention. Suppose after updating, this guy the other time I said the theta 1 2 actually equal to theta 1 3 and theta 2 3, right? Now you've gotten this to be 0, and you've gotten that to be that. Situation where the precision here equal to 0 is trying to say you are not going to have any edge, any arrow connecting S1 and S3. Even though initially, if relationship exists, that relationship is indirect. Then we're going to remove that. But you know what this guy is trying to say? Okay. So the first one that said is equal to 0 mean before observing the rest, relationship exists. But after observing the rest, the relationship disappeared. That is what we call conditional independent. Conditional independent is what is going to make your network sparse. But you know what this guy is trying to say? He's trying to say, even after we have observed the rest, relationship exists between S2 and S3, then we're going to call that conditional dependent. Does that make sense? So that's exactly what you see there. Okay, now I'm moving. Okay, so that's a summary of everything that we've done, and this is actually telling us, the parameter transformation. The beta is just going to be the ratio of that, the negative. Okay, so we are that equal to that. Okay, now I was talking about working covariance the other time. So the working covariance is the one that we use in the algorithm. But how do we get a working covariance? The working covariance equal the sample covariance plus lambda high. And you know why I'm actually adding to the diagonal? Because the variances, we want it to be positive definite. I think you remember positive definiteness, right? Okay, so we don't want to tamper with the variance. We don't want the variance to be less than 0. We want variance to be strictly positive, okay? Okay, I think I've walked it through. So, in the end, if this is a lasso, then you update your covariance block with this. This is the updating. Then you recover the precision, because we're going to recover the precision from the working covariance. And in the end, that is what we got. So the interpretation here is that the lasso solve problem for one variable against the others. Okay, so this is the reason. I talked why I scale it up the other time. Positive definiteness needs to be preserved. That's why we make use of working covariance, why we're trying to shift elements in the diagonal of the conventional sample covariance or by lambda high. Okay, so this is the animated step-by-step version where you are updating. That's the way it's going to look like. Take a look at that. When you finish with this update, go to the next update. That is how it's going to look like. Okay, so let me see. Okay, now when you want to start with your working covariance, lambda has very serious effect. The values of lambda. This is to tell you that when lambda increases, okay, you're actually going to have more shrinkage. Okay, more relationship will disappear when you have a very large value of lambda. And of course, when you have a small values of lambda, you're going to retain a good number of relationships. So small lambda actually going to give us a dense graph, and why large lambda is going to give us a sparse graph. So what I'm trying to show you here is to see that, when lambda increases, okay, let's get a look at what I have. When lambda increases, and of course, the number of non-zero of the diagonal, because in the number of non-zero of the diagonal, if I say non-zero, that is the numbers of the arrows, the numbers of the reconnection, the direct relationship. That number is what I'm talking about. Okay, so that number is expected to go down when the number of lambda increases. So that is what that graph is showing. So because of this, we don't want to we don't want to, because maybe we want our network to be sparse and intentionally use large lambda. When you intentionally use large lambda, there's possibility you could eliminate direct relationship. We don't want to eliminate direct relationship, and what we need to do in this situation is to look for an approach to optimally figure out what the values of lambda is going to be, instead of choosing lambda arbitrarily. Okay, small lambda, a lot of connection, right? Large lambda, of course, few connect. This is dense. This is sparse. Okay. I think I put some R code. My TA is going to walk you through all of that. If you take a look at in the arrow code, at times we could try using the method of cross-validation. I can vary my lambda. Maybe I can, 0.05, 0.1, 0.2, then I can choose, using cross-validation, which one is going to work. Okay? So I think we're going to do that on Friday. Okay, I want to go into more example where graphical lasso can be used. The graphical lasso can be used in finance. It can be used in brain network. It can be used in gene expression. Anything that involves networking. Okay, so pay attention. Suppose we have, suppose the variables are returns on different stocks. Returns from different stock. You have in banking, in energy, in technology, in healthcare. Okay. Now, before you can have this kind of network, okay, the graphical lasso will eliminate any spurious relationship or association. Does that make sense? It's only going to retain the one that is direct. That's what I'm talking about here. Okay, it identifies direct conditional. It's going to, even though I know returns from different stocks may be related, but I'm only interested in those ones that are directly related. I'm not interested in those ones that are indirectly related. And the graphical lasso is actually going to help us with that. And how is this going to be? How is graphical lasso going to be gainful to financial world? It's going to enable them to produce what I call interpretable financial network. Now, it has another example in genomics, where I have several genes connecting. Okay, of course, we actually want to retain direct relationship. Okay, the graphical lasso, what make your network to be dense. When your network is dense, your network is going to be noisy. Okay, and when it is noisy, there's possibility of overfitting. We don't want all of that. We don't want situation where your model will perform greatly on training data and will perform woefully on seeing data. Okay, and that is the reason why we need to bring in graphical lasso in. Let me tell you this: the graphical lasso actually is going to help in situation in a higher dimensional data. Okay, here I said a zero entry in the precision matrix suggests no direct association after accounting for other genes. Okay, I give an example here that look like an exam style example. Please pay attention. Maybe I give you that sample covariance. Please pay attention. Okay, what happens to the estimated of diagonal precision entry as lambda increases? Okay, as lambda increases. You remember what happened the other time? As lambda increases, you're actually going to have sparse graph, right? Okay, so that is that. So and the answer to that question is this. This is the answer to that. In case I ask you in exam, the L1 penalty increases shrinkage. The off-diagonal entries is pushed towards 0. Then for sufficiently large, it becomes exactly 0. So you have a sparser graph to answer that question. Another exam type, look at that. Why is blockwise coordinate descent computationally attractive for graphical lasso? Okay, that is the reason. We don't want to solve the whole full matrix. That's going to be an issue doing that. That's why we don't have it in the blockwise. Okay, then we're going to apply the idea of updating. Okay, and each update reduces to lasso problem. Okay, and lasso solvers are efficient and scalable. Now, another one. Explain the meaning of the partition. The meaning of the partition. This is a precision matrix, right? Okay. The first one, the precision matrix for all other variables except the one you are updating. The theta 1, 2, and there's a connection between the selected variable and the others, and the theta 2, you're talking about the variance of the variable you're talking about. Now, there's another homework sheet. Okay, state the graphical lasso optimization problem and define each type. Write the first order optimality condition. Explain why the diagonal entries are treated differently from the off-diagonal entries. Okay, diagonal entries are where the variances are. You don't touch them. In fact, we normally want to make it to go up. Okay, because we were actually one situation where they're going to be greater than 0, and we can attain positive definiteness. Okay, show that the blockwise update lead to lasso subproblem. Explain the role of turning parameter lambda in one paragraph. Explain why graphical lasso is useful in. Okay, so I think I provided the solution here. This is a graphical lasso objective. That is the first. When I gave the graphical lasso objective, I also, give the definition of term. Okay, we don't just write a model without you telling us what each term represents in the model. Then the first order condition is after differentiating. Okay, after performing the first derivative on that. Okay, then the solution of why are diagonal and off-diagonal entry treated differently. Okay, so you can see the way I answered the question here. I said the diagonal entries must remain positive for positive definiteness. That was why I was adding lambda I. Okay, the off-diagonal matrix entries will be the one that will determine the arrow. You understand what I mean? Okay, then sparsity is mainly meaningful for off-diagonal. We are not sparsing the diagonal. Does that make sense? Okay. Then another one question said, why does blockwise descent lead to lasso? Okay, this is why. Okay, because we are updating one at a time. It's like we're performing a regression problem where, we're looking at this in relation to others. So that's why after partitioning the matrices and fixing all but one row or one column, then the update can be written as that. Okay, and what is the role of lambda? Okay, I told you, the lambda will control the amount that you're going to shrink. Okay, amount of relationship, you're going to shrink. Okay, so I just wanted to see that. When you have a large values of lambda, you're shrinking more. When you have a smaller values of lambda, you're shrinking less. Okay, and of course, all of that has application. I think that is all what I have for you. So, is there any question for me? Any question? Now, what we're going to do on Friday, we're actually going to make it how this is done in R, and also use the approach. I think what I'm actually going to show you on Friday is the way we determine the lambda, and to determine the lambda, it depends on our intention, because there are two serious goals, in statistical machine learning. Do we want to explain or do we want to predict? If our goal is explanation, okay, the way we're going to select the lambda will be by AIC, a BIC, or the extended BIC. But if the goal is prediction, of course, we actually going to use the root mean square error, approach. So I'm going to show you because lambda, the turning parameter, is very, very important. We don't choose lambda arbitrarily. We actually need to have a way to figure out the lambda, because when you deliberately choose large value of lambda, there is high probability you're going to eliminate direct relationship. We don't want to eliminate direct relationship. That's all what I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.